Stanford University.
Hand you over to Dr. Drake, who is going to tell you all sorts of stuff that's going to keep your mind absolutely humming for the next rest of your life. So thank you very much for coming, Frank.
Okay. Thank you, Lynn. It's fun to be here. I was here last year. I guess you're all different this year, I hope.
Well, those of us in the front.
Because I'm going to tell one or two of the same jokes again. It is a pleasure to be here, and Lynn asked me to, in a way, tell you about the history of SETI, how we got where we are, how we actually do SETI. And since I've been with SETI since day one, I've lived through all of it, and what's going to be today is a sort of a stream of consciousness history of what has happened over the 50 years of SETI. As we just mentioned, April 8th is the birthday of SETI. That's the day the first modern search was started. Notice I said modern search. There were actually searches before 1960, and by some pretty eminent people. Nikola Tesla, in the late 1890s, searched for signals from extraterrestrials and actually transmitted messages from a Tesla coil transmitter in Colorado Springs, Colorado. It generated thousands of volts, made everybody's hair stand on end, and sent messages out with very high power. And in fact, he thought he had detected messages from outer space, but he hadn't. He had detected signals which sounded like signals. They weren't. They were natural radio emissions, but they sounded like whistles. And in fact, they are he actually discovered the phenomena we now study these days, known as whistlers, which are low frequency waves which follow the magnetic lines of force in the Earth's magnetosphere. In the early 1910s, Guglielmo Marconi attempted to detect signals from outer space, and he listened and listened. He heard the whistlers also and was impressed, but there seemed to be no intelligent content to the whistlers, and so he decided he hadn't succeeded. Now, both of these did not realize that their experiments were hopeless. There was no chance they could detect signals from outer space because, why? The wavelengths on which their receivers worked in those days were so low that they were below the cutoff frequency in the ionosphere, which means that any signal from outer space would have been reflected from the ionosphere, could not reach the surface of the Earth. Well, it took really 40 years or more before our technology advanced to a state where we could detect signals coming in from outer space, and indeed from the distance of the nearest stars. The nearest stars like the sun, which are about 10 light years away. And in the late 1950s, we crossed a threshold, the first time in our civilization, and I believe this threshold has been crossed in many civilizations, the first time when one could detect reasonable signals across the great distances which separate the stars. And by that I mean tens of light years or more. This came about through the construction of large radio telescopes for the first time, and also the development of some much more sensitive radio receivers. Receivers that were about 10 times more sensitive than the vacuum tube receivers that were otherwise used in those days. When you put that combination of technology together and calculated the sensitivity of the resulting instrument, it turned out to be adequate to detect the strongest radio signals we were then transmitting from Earth on frequencies which would pass through the ionosphere and reach the surface of the Earth. And so for the first time in our history, it became reasonable to search for extraterrestrial radio signals. We didn't have to assume the existence of a super civilization. We never assumed that. In SETI, we always assume only things we know to exist or are permitted by the laws of physics. And so it made sense to search, and so in 1958, 59, we started building equipment, myself and some colleagues, to search for signals from outer space. Now, the paradigm in those days was very naive and limited. We were looking for planets like the Earth, here it is, where there's going to be life like us, which could manipulate tools, was intelligent, and had the ability to build radio transmitters. In fact, to this day, if you're really honest, we don't search for intelligent life. We search for advanced technology. Maybe it's made by computers. We couldn't tell. But we're looking for something that transmits or releases enough energy, maybe purposely, maybe just in the process of doing other things, such that we can detect it with reasonable instruments that we can build across the distances which separate the stars. That was our paradigm. And at that time, until this day, we think about what should we search for? What are reasonable ways for signals to be sent purposely? Or what technologies might be used which would release energy as a side product or byproduct of some enterprise which we could detect on Earth. And this is still, again, an intellectual game. You're all invited to engage in it. And back then, thought was given to using neutrino beams, for example. But if you know anything about neutrinos, you'll realize they're really hard to generate. And what's worse is they're even harder to detect. They go right through the Earth and out the other side without anything happening. So neutrinos have never been a favorite. Nobody's ever searched for neutrino beams. Maybe that's a mistake. Maybe that's the easy way. Who knows? Then there's gravity waves. We have gravity wave detectors, but they can only detect gravity waves that are generated by stars going in orbit at high speed around one another. Very hard transmitter for us to build, and for anybody to build. So we don't search for gravity waves. But then there's the electromagnetic spectrum, gamma rays, X-rays, ultraviolet, radio, optical, infrared, all of that. And all of that is fair game, because in all those cases, one can conceive of transmitters which would send signals which we can detect with our existing equipment. But to this day, we have emphasized radio searches, and I'll tell you why in a minute. There is actually a reason for that. And in SETI, you always have to be very careful not to be anthropomorphic, not to do things just or assume that something's happening in outer space just because we do it or because we do it well. Just because we can build very sensitive radio receivers doesn't mean everybody does that and they'll be sending us radio signals. Maybe they have especially good infrared transmitters, and actually you can argue that's actually more desirable because there's infrared waves traverse the dust clouds in the galaxy without being absorbed. So anyway, back in 1960, because we were a radio observatory, this was in Greenbank, West Virginia, we put together an instrument to search for radio signals. It was capable of detecting the signals we were then radiating in the microwave region from the distance to the nearest stars, and we targeted the two nearest stars like the Sun, the stars Tau Ceti and Epsilon Eridani. Both much like the Sun, both evidently alone in space, which in those days was thought to mean they might have planets. So this was a good place to search. We didn't search for light signals. I should have mentioned that. Light signals are a good sign of the presence of a civilization. And this is the Earth at night, is photographed by a satellite. Looks pretty bright, but in fact the lights here have been enhanced in this picture. But it turns out to detect the lights of cities at night require an optical telescope of about 5 kilometers in diameter. And the best we've got is right now 10 meters. And right now there are people frantically designing and trying to meet the challenge of building a 100-meter dish for light for light signals, but you really need 5 kilometers. So this is presently out of our reach, and nobody with any common sense is going to search for this. But we did search for, this is stream of consciousness. Another thing you have to consider is spacecraft. Should we send spacecraft, and should we expect that they are sending us spacecraft? If you go to the science fiction movies, of course, they make you believe that interstellar travel is very easy. You just call up Scotty and say, warp 7, and the time it takes to do a commercial, you're in some other star system. It's wonderful. But here you have to take serious respect for the laws of physics, because high-speed space travel is extremely challenging. Our present spacecraft go about 10 kilometers a second in speed. 10 kilometers a second, that's 1/30,000th the speed of light. takes you a long time, 30,000 years to go 1 light year. And so to get to the nearest stars, it takes hundreds of thousands of years. And we have spacecraft which have now left the solar system, but they're not going to get anywhere for hundreds of thousands of years. To get anywhere useful, you need to go nearly the speed of light. And to do that, you need propulsion systems that we don't have. But I've shown here the ultimate propulsion system. Here it is, very simple design. It's a rocket that just has 2 tanks. One has ordinary matter. That can be water. Anything will do. The other is antimatter, which is matter, of course, where the atoms consist of negative protons and positive electrons. And what we know, we actually created this in SLAC, some antimatter. And what we know and what was theoretically predicted is that when matter meets antimatter, there's a total annihilation, all the mass converted into energy. And so that's the ultimate source of energy. And that's a way of making a rocket. Now, when you make this this fusion of antimatter and matter, the product is actually gamma rays, which of course could heat a gas, but gamma rays are a pretty good propellant too. Now that may look like a delta to you there, and that's because, this is, as you can tell, this is a dusty slide. It's a leftover from the era of the Cold War, when we were first thinking about this. And we didn't want the Russians to know that it's really gamma rays that comes out of this thing. So there's these mysterious delta rays that come out of here. There are certain technical problems, like where do you get antimatter? It's really hard to do. And how do you store it in anything? And particularly, what do you make the rocket out of that can simultaneously hold matter and antimatter? And we don't know what that is, but we at least have a name for it. It's called a mutabilium. And a thing like this can actually approach the speed of light. And there's been actually detailed designs done, actually here in Palo Alto, back again during the Cold War. 4-stage rocket. This is designed to go 7/10 the speed of light to a distant world, land, take off, and come back to Earth at speed of light and land. Now, why 7/10 the speed of light? That's the speed at which the relativistic time dilation makes the travelers think they're traveling the speed of light. That is, time is slowed down for them sufficiently that it takes them in their watches 1 year to go 1 light year. So that's kind of neat. Anyway, this is staged to minimize the requirement of mass, and here we see it. This is with a payload of 1,000 tons. So this is a spacecraft that's about the size of a 737 airliner, something like that. And the other numbers you see here are the mass of matter and antimatter you need as fuel. And the total is 33,000 tons, so 16,500 tons of antimatter. Well, there's no antimatter mine. You have to make that in some machine, and that will take at least as much energy as is in that. That's with 100% productivity, which of course won't happen. That turns out to be 500,000 years of the total electric power production of the United States at the present time. 500,000 years. So you have to shut down America for 500,000 years to make this trip. And maybe when you get there, nobody's home, you know. You get back in the spacecraft and you come back home at the speed of light and say, gosh, we're sorry. We took some pictures, but all we saw were rocks. Well, you can hypothesize simpler missions. For instance, if you wanted to go to a star 10 light years away at 1/10 the speed of light, so it's a 100-year trip. I don't know if you'd really want to do that. You got a 737 size spacecraft with maybe 40 passengers in it. 100-year flight, so most of you wouldn't live to get there. Your children, you'd have to have children born on board and all of that. And it turns out that you redo all this equation. It doesn't take nearly as much energy. It only takes 200 years of the total electric power production in the United States to fuel the thing. And by the way, that's for a one-way trip. You don't get to come back. You've got to find some nice place to live there. Well, would you want to do that? Right, 100 years in a little airplane, watching the same movies over and over, eating, old sandwiches that they sell you for $6. Like that. And there's one other. Well, there's one other problem. You don't want to go, I can tell.
The thing is, you'd find people that would want to go.
There would be people. Who would go? There are 3. You better note who those are, because they're,
Sign it up, Jesse.
you got some slightly.
Hands up again.
There's one other problem. I mentioned a tenth of the speed of light, and there's something that in the science fiction nobody ever takes account of, and that is if you're going more than a tenth the speed of light, if you hit a little pebble, the energy release is the same as if that were a fusion bomb. You get the MC squared out of MV squared over 2 that you get out of that is equal to MC squared over 0.007 MC squared, which is what you get from nuclear fusion reactions. So a little pebble like this will destroy your spacecraft. One hit. So it's very dangerous. It doesn't just cost much and cost a lot, but take a long time, but it's very dangerous. And this is one of the objections to or possible solutions to the Fermi paradox, which I'll come back to later. You know, why haven't they come to Earth? Well, I just told you why they don't come to Earth. They can't turn off their planet for hundreds of years. And even if they did, the mission would get destroyed along the way, and it'd be a big waste of time. So we searched for radio signals. And this is what we used in 1960. This is the team of people who put all this together when we had a reunion about 15 years ago. It used a 25-meter radio telescope at Green Bank, West Virginia. Still there, still operating. Old telescopes never die. They're good. And here's the sophisticated equipment that was used. 4 racks of equipment. It constructed a system which could monitor 1 radio channel at a time, bandwidth 100 hertz. It could be tuned across the spectrum, and it was built specifically for the frequency of the hydrogen line, the basic line of hydrogen caused by its hyperfine nuclear transition at 1420 megahertz. Now, why that? 2 reasons. One good reason, since it's the fundamental radio frequency of the most abundant element in the universe, it was thought that it might be a frequency where civilizations met each other. There's always this problem where what frequency do you look at? And how do you meet a friend in a distant city when you can't arrange to meet them in advance? Well, you don't just go wander around. You go to some prominent, well-known place that you both know of, and that's where you meet. And the hydrogen line is that in the radio spectrum. So that was a good reason for doing that. In fact, that same frequency has been used in almost every search since. The other reason was that it was realized that searching for extraterrestrial life might be ridiculed or criticized, and this was being done at a national observatory, taxpayer supported, and we didn't want anybody to say that taxpayers' money was being wasted searching for little green men. Couldn't have that. That would be really bad, and the National Science Foundation would have been really upset. So we made the device for this frequency because then it could be used to observe the hydrogen line from neutral hydrogen gas, and specifically the Zeeman effect in the hydrogen line. Well, all vacuum tubes. All but one of you, I think, is so young that you don't realize there was a time when there were no transistors, that everything was vacuum tubes. Well, I don't know, you're just barely, just barely. And there was also a time when there were no computers. That's probably big news. And there are no computers here. They didn't exist in that era. The data was captured on a pen and ink recorder, which is right here. The frequency was selected by a radio amateur receiver, which is up here, because it was easy to put a motor on the tuning dial and tune that way. And for those of you who know something about radio, this served as the intermediate frequency system for the thing, and it listened to 1 frequency. And just because we were optimists, we had a tape recorder here. Some of you may have seen these in a museum. Reel-to-reel tape recorder, which was ready to record the voices of the ETs when we found them. And this is what we searched with for 200 hours for 2 months, starting on April 8th of 1960. Actually, we discovered something the first day, which was quite a shock, which is we heard a pulsing sound, because we had a loudspeaker too, connected to all this. We were really optimistic.
Did the telephone to the White House too?
No, we didn't have the White House number ready. We weren't that crazy. We heard a pulsing sound going. Choo, 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 choo. We never heard that before, and we got very excited. And before we could establish where it was coming from, it went away. And we spent weeks looking again at that same frequency, same place in the same star, Tau Ceti, and never heard. We did hear it again later, and determined that it was actually coming from an airplane flying around, and it was evidently a military plane testing a radar jammer, and it thought by going to the wilds of West Virginia to be someplace where nobody'd ever capture its signal, but we did. Well, this stimulated about by now 100 other SETI searches, all similar to this, except with ever improving equipment, particularly receivers which receive many more channels, much more sensitivity, and in particular built-in computer hardware and software which searches through the data that flows out of these things for signs of signals. Because by today, our radio systems don't look like this. They have 100 million channels, typically, and you read them out every second. You've got a new data point, 100 million data points a second, and there just aren't enough students in the world to go through all this stuff and see if there's anything there. And that's been going on since. Now, why was this a good idea? I told you why the hydrogen line was a good idea, but there was something else we were aware of which to this day favors radio frequencies for searching. And this is a graph which I always like to show because I'm sure it's been shown millions of times in the universe, and it looked exactly like this. It's just the lettering was different. And this is a graph which shows the level of natural noise in the cosmos as a function of frequency in gigahertz. So here's 1/10 of a gigahertz. That's the frequency of an FM radio. There's 1 gigahertz. That's typical of cell phones. Radar systems are in here. Communication of television to people's homes is right out here. And so that's where we are in the spectrum. Now you look at this, and what we know, and every civilization will know, is that there are 3 sources of noise in the universe that matter. One is radiation from electrons orbiting in the magnetic fields of the galaxy. They all have them. In our galaxy, it leads to noise which follows this curve here. It rises, becomes very strong at lower frequencies. Notice this is a logarithmic scale. The second source is so-called quantum noise, the fact that electromagnetic radiation comes in photons, and as you go to higher frequencies, it takes fewer photons for a given power level, and they sort of pitter-patter on like rain on a roof, and the pitter-patter gets stronger and stronger as you go to higher frequencies. So this is quantum noise, and this has been converted into a temperature scale, which you can do just by taking h nu over k for the photons. Interestingly, there is a third source of noise, which we didn't know in 1960, but is there, which is this, which is the so-called 3-degree blackbody radiation, the remnant radiation from the fireball which formed the universe. And it's kind of interesting that that plays a role in selecting what frequency you should search for. Well, you add these all together, and you have noise which cannot be eliminated by any technology. And you get the curve you see here, and it has a minimum here. And we know this, and all civilizations will know it. They all are subject to this. And the laws of thermodynamics say there's no technology that can escape this noise. It's there to minimize or limit your sensitivity. And this says then that the ultimate frequencies for communicating in space are here in the microwave region, what we call the microwave region. And that's true for every civilization. And we, in fact, exploit this. As I pointed out, our radar systems are here. Our direct transmissions to Earth are here. And this is so we can do those things cheaply. We can use 18-inch dishes instead of 3-meter dishes on our roofs to collect television direct to home, and so forth. All our communications with spacecraft in NASA are with the frequencies right in here. So this is where we searched, and why people have favored this region for all of the last 50 years. Now, recently we moved on to looking for some light signals, and I'll show you why, because there's a special situation there. In any case, there have been, I said, over 100 searches, and along the way we also developed this thing, which Lynn says I must tell you, although you've already heard about it, because it's got to be on the video. And this was invented back in 1961 in a follow-up meeting to the first search, which was called Project Ozma, in which I was asked by the National Academy of Sciences to convene a meeting to discuss this whole subject and see just what people thought. And so I convened a meeting of all the people in the world who I knew were thinking about extraterrestrial intelligent life, all 12 of them. And they all came. And we all met in Green Bank. And a day or two before the meeting, I, as the convener of this thing, the entire local organizing committee, decided we need an agenda. We aren't just going to get in a room and start talking. We have to have themes. We have to have subjects for the various sessions. And so I thought about what is it we need to know about to predict N sub t, that's the total number of detectable civilizations in our galaxy. What do we know? And what we know is, in a way, revealed to us by the history of our own solar system. How the solar system came about, how the planets came about, when they are habitable, what were the chances of life, etc. So it turns out that you need 7 factors to describe that whole picture, the whole history of the evolution of the solar system, and they can give you N sub t. Now, how does this work? We're after N sub t, and we start with the rate of star formation. Of course, the more stars you create, the more planets, the more intelligent civilizations there will be. And they have to be suitable stars, ones that can give rise to life. This is actually a low figure. These are old figures that have been now improved by recent observations. About 10 per year is right for that number. Now you want to multiply that by the fraction of stars with planetary systems. That'll give you the rate of production of planetary systems. And this was the guess back at the 1960. Today we know that it's at least 0.5 and probably greater than that. Now, in each system, there will be some number of Earth-like worlds. Now, by that we mean habitable worlds, where conditions are suitable for life, which we've come to understand today means temperatures on the surface between the freezing and boiling points of water, and you've heard all about that. And that is typically 1 to 3. In our own system, that includes Earth. Would have included Mars if it had been just slightly more massive and could have held an atmosphere. Maybe you can include Europa. There's 3 right there. So it's of the order of 1 to 3. Then you multiply by the fraction of those Earth-like planets where life develops. And that is, I've given the really pessimistic number, which nobody believes, that's much closer to 1. And that's based on the fact that our chemists have found a multitude of chemical pathways to the development, the formation of the molecules basic to life. Purines, pyrimidines, amino acids, and all that. Now, we come to well, they have to multiply this next fraction, which is the fraction of these on which intelligence develops. That one right now is still problematical. There are arguments in all directions. There's some people say it's very small, that it was a freakish event that we are here thinking. Other people look at the fossil record and see that the size of the brain has always increased, and tells us that eventually you will always, given enough time, develop an intelligent species. So this is slightly vexed, and of course I lean to the figure 1, and I do reject an argument which is made by some eminent paleontologists, which I think is just really showing a lack of understanding. And the argument they make is, well, look, there have been, in the history of the Earth, there's something like 300,000 different species of things, and only 1 became intelligent. Doesn't that mean the chances are 1 in 300,000? And this should be 1 in 300,000. And what that does not take into consideration is that it takes time to produce intelligence. And there will always be 1 species that becomes intelligent first. And we'll look around and discover, whew, there's only 1 of us. Does that mean we're really improbable? No, it just means we're the first. And given enough time, there would be more intelligent creatures. And if we left the Earth for whatever reason, bad reason probably, there would be other intelligent creatures. It may take another 1 billion years or so, but they would come. And people always, at this point, they usually ask me, well, what do they look like? And the obvious answer is that the chimps will become intelligent, or the bonobos, I guess they're called, the primates that are closest to us. Actually, living here in California, my prime candidate is raccoons or squirrels. They both outsmart us. They get into bird feeders. There's no stopping them. Anyway, there are creatures standing. The squirrels stand up on 2 feet and can use their hands. You know, they're just watching us. They're ready to take over. Just watch. They're waiting. They're going to pounce one of these days and take over the earth. And then we have to multiply with a fraction of intelligent beings which develop technology. And again, this is perhaps problematical. It does depend on your ability to manipulate tools. I don't think you can have technology on a totally water planet because you need metals, I think. You need fire to build things that can release energy in amounts which can be detected across interstellar space. But on Earth, amongst us, technology has been developed independently 5 times, so that is not a freak event. If you have the ability to manufacture tools, it's going to happen. So this could be one. Now, multiply all those together, and these numbers, and you'll get something like those first 6 factors all multiply together to be 1. That makes it really convenient as a rule of thumb. And the last factor is the lifetime of a civilization with an ability to communicate in a way you can detect. Those words should have been added. Because what you have here is this first 6 give you the rate of production of detectable civilizations. The total number is equal to that times the length of time they exist on average. Just like the student body here on this campus, the number of students here is equal to the number that enter each year times the average time they stay here. So then this last factor is the really problematical one, because the only example we have is ourselves. We have been easily detectable since 1950 through our television broadcasts and our high-power radars. We are detectable before that, by the way, by the lights of our cities at night to anybody who's got a 5-kilometer telescope. So, you know, it gets to be a little problematical just how you define what this factor is. It's usually written with a capital L. But the end result is when you multiply all 7 together, you get the number of detectable civilizations. And we don't really know many of those factors accurately. And in science, when you don't really know something very well, it makes it more believable to write it in fancy letters. So that's why we have it this way. And it's easy to remember, and it's something like 1 times the longevity of civilizations. And if you happen to see a car going around with this license plate, that's me. It's the only way I could fit the equation on a license plate. And it's actually making a political statement because it's implying that intelligence is common and that L is a long time. Yeah. So, since those early days, we've gone on to much larger telescopes and other projects. This is the 85-foot telescope at Harvard University, which was used for many, many years to search continuously for signals. One day it had a structural failure and has since not been used. You can't quite see it. There's a little boy standing here. I don't know where he went. But he's only 4 years old. He was put there to make it look bigger than it really is. And we've gone on to the giant telescopes. This is the largest in the world, the Arecibo Radio Telescope in Puerto Rico, which has been used in many SETI searches and is used continuously now to collect the data that's used in the SETI at Home program. How many of you do SETI at home? My goodness. Usually half the audience puts up their hands. Well, you should learn about it. It's on the web. It's free. It's a program you download. It's SETIathome.org, I think. And once you've loaded the software, the data, which is all accumulated at UC Berkeley, will be sent out to you in packets, and the program will automatically search through the data taken at Arecibo for signs of an intelligence signal. And in the many years now, it's 10 years at least that this program's been running, they've seen about 200 candidate signals. And what is then done is to go back to the telescope, look at the same place in the sky on the same frequency to see if the signal's still there. Never has been yet. We don't know what that means. We originally thought that just meant it was all the stuff they detected was just statistical accidents or radio interference. Now, as you'll hear from me later, we're beginning to think that maybe the signals are there, but they're usually transient. They're not there all the time. So they'll be there one day, and you can maybe have to wait a year before the signal comes back. So we may have, in fact, have detected an ATI and did not recognize it. Well, this telescope has a reflector 1,000 feet across, 300 meters. It's by far the largest on Earth. It focuses the radiation on the suspended platform, which is about 450 feet in the air, suspended upon the three towers, each of which is 10 feet taller than the Washington Monument. The central structure that you see there is the size of the next largest telescope. Here it is. And you can get some feel for the size of it by this railing that's here. It's actually 100 meters long, the size of the next largest telescope. And in this particular radome is actually two reflectors, one of which is a 60-footer, which is used to take the radiation, the captured radiation from the big dish, which is spherical in shape, therefore does not focus radiation to a sharp focus, and corrects the radiation for the spherical aberration, so that it does come to a perfect focus. And there's a combination of, at present time, 7 energy collectors in there which collect the radiation, allows you to do a radio image of the sky, but primarily gives you the enormous sensitivity to detect signals. Now, also in here there is a radar transmitter, which transmits a peak power of 1 million watts. Keep that in mind. We're going to see some more of those transmitter powers in a while. 1 million watts. Now that 1 million watts when focused into a narrow beam, and the beam is about 2 minutes of arc, a little, almost the same as the acuity of the human eye. When focused into a beam of 2 minutes of arc, it is so bright that it outshines our sun in the direction of the beam, and by a factor of about 1 million in the radio frequency, which is in the microwave window at about 2 gigahertz. That signal is easily detectable by a similar instrument from anywhere in the Milky Way galaxy. Anywhere. And that shows us that we can detect other civilizations. They can be, if they only have to be like us, and we can detect them. Now they have to have the thing aimed at us for that to work, which of course greatly decreases the chances of success, but that's another reason why the signals may be transient. The signal may be aimed at you only occasionally. So this is our signature to space at the present time, and tells you that in fact a search is plausible. It's plausible that you could detect something with these searches. This is just a picture of the reflector. It's got 7 acres of surface panels, each actually curved to the curvature of a sphere, which is 870 feet in diameter, and and accurate in the placing of the surface to 1 millimeter. That's what it takes to get this full possible gain of this instrument.
What is the surface made of?
The surface is aluminum mesh, and the focus isn't good enough to see this, but it's perforated aluminum sheets, and they are sitting on aluminum beams that are bent to the spherical shape underneath. And there are 38,778 of them. Thank you for asking.
Feel much better.
38,778 surface panels in the AAC reflector. Yeah. Yeah.
So maybe why it was chosen to put it in Puerto Rico?
Good question. By the way, interrupt me and ask questions. I said this is a stream of consciousness thing. And why is it in Puerto Rico? It was originally built following the launch of Sputnik. The launch of Sputnik scared the world, and particularly the U.S., because there were paranoid visions of the Soviet Union putting nuclear bombs in orbiting spacecraft like Sputnik, and in a nuclear war just deorbiting them so they would fall on Earth, in the U.S. So they wanted a way to detect the presence of what are called black satellites to this day, because what the idea was that these orbiting bombs would be painted black on the outside so they wouldn't reflect any light, so you couldn't see them, and they would have radar absorbing substance on them so you couldn't detect them with radar, so they would be invisible. And this was really scary, and there was a good reason to be scary. That would be a dreadful weapon to have up there. And they wanted some way to detect these. So there was a report, which ultimately turned out to be wrong, that behind Sputnik they could see a trail of ionization. Sputnik was going high speed through thin atmosphere and was allegedly ionizing things and creating a trail of ionization behind it. And ionization does reflect radar. And so what was wanted was to check this out and to build a radar so powerful that it could detect these ion trails, and in this way provide a means to detect any black satellites. The theory was done as to what it would take to detect those ionization trails, and it turned out to do it you needed a 1,000-foot telescope as the transmitter and receiver, and using a 1 megawatt transmitter. And that was why the instrument was started. But of course, why is it in Puerto Rico? That's for another reason. This was all done by Cornell University at Electrical Engineering Department. The Department of Defense was eager to pour all the money as required into this. But along the way, the Arecibo Astronomy Department sort of put up there and said, hey, you know, we could use this to do radio astronomy. You know, this would be pretty neat, a 1,000-foot radio telescope. And the original inventors didn't like this idea much because they knew it was going to get and sort of slow things down while this was thought through. But eventually it was decided, yeah, we'll make this thing so you can look in different parts of the sky. Well, it was also to realize, hey, you could use this thing, it's going to be a radar, to make radar studies of the planets. So we need to put it somewhere where we can direct the beam of the telescope at planets. Well, the dish is spherical, and and it looks in different parts of the sky by moving these things on this beam, and it can as a result it can only look within 20 degrees of straight up. So if you were going to look at the planets a lot, you had to put it where it would be able to see the planets as much as possible. And the planets all hover around the ecliptic, and the ecliptic goes from about plus 20 to minus 20 declination, which means over minus 20 to 20 latitude. So ideally, the telescope needed to be on the equator. But then, since this had sort of a military aspect to it, they decided it had to be in U.S. controlled territory. So we looked for, I didn't do it, people looked for a place that was U.S. controlled and was as close to the equator as possible. And the candidates were Hawaii, plus 20 latitude, Puerto Rico, also plus 20 latitude, American Samoa, and Cuba. What? This was 1959, year after Sputnik. In those days, Cuba was our friend, and it was almost put in Cuba. And what was done was to get an expert, which Cornell happened to have, on identifying landforms from aircraft photographs. And they looked for a place in any of those places I just mentioned, which had a bowl the right shape just to minimize the cost of creating the big reflector. And it turned out that this bowl here, if you saw the original aerial photograph of it, almost looked man-made. It's almost a perfect spherical shape. There was almost no carving needed to make it so it would hold this big spherical bowl. And this bowl, by the way, is 200 feet from top to bottom. It had to be a pretty deep bowl to do this. So it was chosen, selected to be in Puerto Rico for the reason I just gave you. And that's why it's there to this day. Very hard to move. I don't think it's going to go anywhere. And there's interesting things along the way people realized, such as what would the Earth look like to extraterrestrials. And the main sign of our existence were our television broadcasts, still are. And actually the television transmitters in those days and today beam the radiation out towards the horizon, because that's where the receiving antennas are, which means that most of it goes off tangentially to the surface of the Earth where the radar transmitter is. And that means that when the east coast of the U.S. is rising for a location, it will see the transmitters. They will be right at the edge of the Earth, beamed at them, as they the people in outer space will see the transmitters right at the edge of the Earth because they're beamed at them. And then later, when the east coast sets, You see it when it's the other way around. So there's this sort of pancake beam rotating with the Earth, and twice a day it crosses everything in the universe and makes these spikes. And there's similar peaks for Western Europe and for the East Coast and the West Coast of the U.S. And then there's subsidiary peaks for the other minor places like Europe. You know, of course, that's all changed. This is an old diagram. It's never been really brought up to date. But it meant the Earth would have looked like a sort of flashing light in the sky. Slowly flashing, but pretty good evidence that there was an intelligent civilization there. And also people point out you could actually find out interesting things like that there are different political regions because the frequencies used would be different from one area to another. The form of the television broadcast would change from place to place. And you could even tell when there are storms, believe it or not, because the storms shake the TV antennas and introduce a Doppler effect into the transmitted signal. So you could learn, and also, of course, when the signals appear and disappear, locates their position on the planet. So you can actually map the planet, the cities of the planet, or the transmitter locations of a planet, and the weather and all of that from this. So this is all very interesting. Still a possibility. And once we get the ability to see television stations. Now, along the way, as all of this was going on, 100 searches, some people started thinking about what might the signal look like. And a way of determining that is to try to design your own signal. It makes you think about what is a good signal to send. If you're an ET civilization and you want to send something interesting and conspicuous to another world. And the first thing that was sent was a plaque, which is on the Pioneer 10 and 11 spacecraft. It's about the size of a license plate, actually. And it's in the form you see here. As I say, it's about so big. It was actually made in San Carlos, down the coast from here. There's a little shop there. You can go and you can buy replicas of this, duplicates. They have the die. And it's very nice. They have them mounted on nice hardwood boards. And when you go in the place, what it makes mostly is golf trophies. But along the way, they made these, which are the signs of our existence in outer space at this time. And this was designed by Carl Sagan, his wife, and me. And it has on it several things. The weirdest thing is this, which looks like a 14-legged spider. And this is actually a map showing the location of the Earth with respect to 14 pulsars, pulsating radio sources. And you can't see it, I'm afraid, in this. But these are binary representations of the pulsing periods of those pulsars to identify them, because each pulsar has a unique period. And up there is the hydrogen atom in its two lowest states to indicate that that gives you a scale of length. It's the wavelength of the hydrogen frequency. And it gives you a time scale, the time scale, one period of of the 1420 megahertz radiation. Down here's a sketch of the solar system, size of the planets given in terms of the wavelength of, which is 8 inches, of the hydrogen radiation. Little sketch here showing the spacecraft left planet 3 and was accelerated by passing by planet 5, Jupiter. And here's what we always think are the most interesting things, which are us. The extraterrestrials want to know what we look like. And so here we are with a spacecraft behind to give scale, but the size is also given here in terms of the wavelength. And a typical man and woman, which provoked a lot of interesting reactions, perceptions of this, which depend very much on the perceiver. It's a very interesting psychological test. The artist, which was Linda Sagan, a woman, tried to incorporate all the basic characteristics of different ethnic groups on Earth. I don't know, maybe we can see it better here. Yeah. So the woman has Asian features, the male has Caucasian features, but supposedly black hair, although it doesn't look very black to me. The man is taller, and these people are the average height of humans on Earth at that time. The man has his hand up. Now that's supposed to be a greeting, but is it? Does it look like an aggressive gesture? He's ready to hit somebody or something. And the fact that the woman is slightly smaller than the man was taken by some feminists to suggest that the woman was standing behind the man in an inferior position. But if you look at her feet, she's not. She's right alongside. But it was interesting that people saw this with regard, usually interpreted with interpretations which were things that they were repelled by. They weren't excited. They didn't say, hey, it looks just like me. Instead they said, it doesn't look like me. I showed this on Canadian television once, on the equivalent of the Today Show on Canadian television. And when it was over, the entire organization was in a frenzy. Because it turned out this was the first time naked humans had ever been shown on Canadian television. And they thought there was going to be a furor, they were all going to lose their jobs. But it didn't happen. It didn't happen. Later, we actually sent a radio message to space. This is the so-called Arecibo message in 1974, sent on April 16th, 1974. It's 36 light years from Earth now. So, you know, a lot farther than our spacecraft. That plaque I just showed you is just out beyond the orbit of Pluto right now. It's at 100 astronomical units from the Earth. That's actually twice the distance to Pluto. But this is 36 light years out. And it consisted of a series of, shown here, zeros and ones. It was two tones, separated by 75 hertz, sent in the microwave band. Well, you look at this now, whoa, what do we make of that?
That's incredible, because it looks just like the essay questions for the final.
Well, I can give you one of these for the final.
Yeah, please.
When I used to teach this same course, I always put one of these on the final. But once I tell you how to decipher it, it's not hard. And your first glance when you look at it, oh my God, what are we going to do with this? You know, what is it? Is it a picture? Is it a message? Is it Morse code? Is it some coding of some language that we don't know? Well, it may be, but there is a way to do this which makes them decipherable and understandable. And that way to do that is to count all these characters. I hope some of you have done that by now. I'll help you. Some of you probably are only halfway through counting. There's 1,679. Well, that's interesting. That's a weird number. Well, the hint here is that this is how the extraterrestrials are telling you what this is. You find out that a little bit of math that 1,679 is the product of 73 and 23. Two prime numbers. Oh boy. And which means you can break this thing up into 73 groups of 23 characters or 23 groups of 73 characters, but no other way. The implication is that this is actually a two-dimensional message, and you should break it up in the way I just showed you. There are two options. And if you break it up into 23 groups of 73 and just write them one under the other in a raster, you get something that looks like a really bad crossword puzzle. But if you put 73 groups of 23, you get this. And these are each line is 23 characters across. And by the way, of course, they weren't in color. The colors are here just to make it easy to explain. But it would have been in black and white. And when you see this, obviously this didn't happen by chance. You've done the right decryption. You've got the coding system. That's step one. That's the easy part. Step two is, what does it all mean? And because the information content is so small, you have to get some real experts. And if you do, it can all be interpreted. It can all be brought to light. And when this was first put together, it was test marketed on a whole bunch of professors. None of them got it all. But the ones with the right specialties did. The top row of characters in white are the binary numbers 1 through 10 with a parity bit added. It's a thing that's done in computers. In this case, they're put there to tell you where the start of the number is. That allows you to interpret the red group, which turns out to be the numbers 1, 6, 7, 8, and 15. That's the big mystery. 1, 6, 7, 8, and 15. Anybody know what that is? Does that ring a bell?
Numbers? Yeah.
Yeah. What are they? 1, 6, 7.
Hydrogen is one, carbon
Yeah, carbon. What are the others? There's three.
Phosphorus.
1, 6, 7, 8, and 15. Atomic numbers, not atomic weights, it's atomic numbers. 1, 6, 7, 8, and 15. Hydrogen, carbon, nitrogen, oxygen, and phosphorus. The stuff, yeah, hey, you got it? It's what makes up DNA. And these green things are in fact the chemical formulae for molecules. And you have to sort of really think about that. But it turns out that these here are the formula for phosphate. This is the formula for deoxyribose. So you've got a chain here of phosphate, deoxyribose, which is the ladder of the DNA molecule. And these turn out to be the formulae for adenine, guanine, cytosine, and thymine, the purines and pyrimidines of DNA. And this shows the whole thing is wound into a double helix. So it's describing crudely DNA and should be recognized by that. You know, not in 2 minutes, that's all I gave you here, but if you gave all the biochemists in the world this thing and told them you got a month to solve it, certainly they would. This is a big number, it's 4 billion, which is the number of codons in the human DNA. So it's telling us, in a way, giving a measure of our evolution, the complexity of our genome, and it winds into a sketch of a human being, as best you could do here. And the human being's size is given here, again in the wavelength of the message. This is our population, at that time about 3 billion. Down here is a sketch of something, which astronomers all spot pretty fast. It's the solar system. With planet 3 displaced towards the human to show that that's where we live. And down here is something that's usually hard because it's upside down. It's a telescope focusing rays to a point, to a focus. And its size is given here, 300 meters, which is the Arecibo telescope. The size of the largest telescope on Earth, giving a measure of the size, the quality of our technology, and also the size of the telescope that sent the message. So that's the Arecibo message. It took 3 minutes to send. And by the time the last characters were being sent, the first characters were passing the orbit of Mars. It just shows you how much better this means of communication is than spacecraft. 3 minutes to go to Mars. It takes 3 months at least with the speediest spacecraft we have to do that. This was followed by a much more complicated message, which is a phonograph record, which is on the Pioneer 10 and 11, or not, no, the Voyager 1 and Voyager 2 spacecraft. And this is the spacecraft, and right here you see a gold box, gold-plated box, which has in it, this is the box up close, it has strange hieroglyphics on the cover, and the strange hieroglyphics are there to tell you what to do with what's in the box. And what's in the box is this, which is a long-playing phonograph record. Now that's, of course...
Has anyone ever seen one of these before?
Few of you have seen those, yeah. You still can find them in your parents' attic and places like that. This one is metal, gold-plated, and two-sided, and most of it is music, Earth's music, picked out by a committee of eminent musicologists. It includes everything from Brahms and Beethoven to Blind Willie Nelson and folks of that era. This was 1977. Interestingly, the Beatles are not on here. The Beatles were at their peak about then, and they're not on here for an interesting reason. The musicologists desperately wanted to put a Beatles piece on here. And they went to the Beatles and said, please, we want to immortalize you. You will live for eternity, and there will be a record of you for eternity in outer space. He said, nope. It's copyrighted, and we don't release our copyright to anyone. And in fact, they stuck by that. And so the Beatles aren't on here, which they're to their loss. And anyway, this is launched. It's on the Voyager 1 and Voyager 2, which are actually the most distant spacecraft from Earth right now. Now, the technology had moved on in the radio. We've gotten to our own computer chips. This shows you one of the computer boards. Now, this is from the era of about 1990. And it has specifically designed computer chips to allow us to construct a multi-channel receiver at low cost, and this was built for Project Phoenix, which was a joint NASA SETI Institute project, which started in the year 1992 on the 500th anniversary of Columbus's discovery of San Salvador Island, which you have to be careful to be politically correct. It was the discovery of America by people from Southern Europe. That was what that was. And this is what the equipment, still 4 racks of equipment, but now this one could do about 10 million channels, and it did have the computer hardware and software to search for the signals which we expected to come from the extraterrestrials.
Now, is this still at Arecibo, or is this at Berkeley?
It's all been cannibalized. It doesn't exist anymore. It's been replaced. This is a typical screen from a monitor screen when you're observing to make sure everything's going right. What you have across here is typically 600 different frequency channels, so only a small fraction of all of them. And each horizontal line is 1 second's worth of data. And where you see a bright spot, it means that during that second in that channel, there was more than the average radio power. And most of it is noise, of course. This slanty line you see here is the signal from a Pioneer 10 spacecraft, which at that time was out about the orbit of Pluto and radiating 1 watt. So easily detected. It just shows the sensitivity of our equipment. And the slanty line is very important, as it turns out, because what makes it? Does anybody have a theory? Anybody explain why that line is such that the radio frequency is, in fact, well, this is the newest data, that's the oldest data. So the newest data is, the newest data is at the top, the oldest data is down here. This is called a waterfall plot because it moves down all the time. So the newest data is at a lower frequency than the oldest data. Okay, make a guess. Sure.
Is it the Doppler effect?
Well, that's one guess. What do you think? Doppler effect. Yeah, it's the Doppler effect. Good.
I should point out that Dr. Drake was dean at Santa Cruz, so this is your chance to show him what Stanford students are like.
Well, they just did. 2 of them at once.
Yeah,
and I think some of the others had gotten it too.
I'm sure.
And if you think about it, it's not totally obvious until you think about it a little. The frequency will always go down with time because of the changing Doppler effect. And that's because the Earth, the actual source of the changing velocity is not the spacecraft being accelerated. It's going along at a very steady rate. It's that the Earth is rotating and the telescope is moving with the Earth. And if you just sit down for a minute, you'll see when the Earth rotates, it always has the effect that the velocity vector component towards the spacecraft is always becoming less. And so you always get a growing redshift to a lower frequency. Now that turns out to be very valuable because we use this in all of our searches nowadays to identify true extraterrestrial signals. Any signal from Earth will not drift in frequency. If it's in space, if it's in a spacecraft or something, it will have some weird drift. But you can predict exactly what the drift should be due to the Doppler effect of the rotation of the Earth. And if that's the drift you see, it means the source of the radiation is fixed with respect to the stars. It's a good candidate for an extraterrestrial signal. And that's our main diagnostic. And we need that because whenever we observe in any given record, with all the channels, you typically just take at least 100 signals. And they're mostly from Earth, of course, but you need a way to find that out quickly, and this Doppler effect is a way that's done. Now, in the late 1990s, it was decided that we needed more observing time. SETI was being conducted at Arecibo, other places, but almost in all places as guest observers on somebody else's telescope. And for instance, at Arecibo, the SETI project had 20 days a year, so very slow going and very inefficient because you'd set the equipment up, get it all running, you'd observe for 20 days, you'd go away, come back a year later, and everything was not working anymore. You'd have to spend a week getting it all operating again. And so a decision was made to, if we could, find the money to build a dedicated radio telescope for SETI. And it needed to be big, maybe not as big as Arecibo, but sort of in that class. And how do you do that? Well, Arecibo, to duplicate Arecibo would take more than $100 million, and we didn't have, nobody was going to produce that kind of money. And the idea was developed to make a big telescope by taking many small telescopes and connecting them together so that the radio waves captured by all of them are eventually brought together in phase, as we say, in synchronism, so that it created the same effect as the focusing capability of a telescope. A telescope, when you really think about it, what it does is take all the captured radiation and bring it together at one point in synchronism. That's how a telescope works. Now this was going to do it not with light being focused by a reflector, but by correcting the path lengths of the signals in some way in a computer. In older times it was done by using different lengths of transmission lines. So what you see here is the first effort at this, and this was a prototype array to demonstrate this could be done. It was built not far from here in Briones Park. If any of you live in Orinda or Lafayette or Walnut Creek, it's between, it's a nature preserve that's just back of Berkeley in the hills there. And, and this was a case of using small dishes. In this case, the idea was to exploit the fact that at that time, this was about late 1990s, there was a huge industry building small dishes for people to use to collect television from satellites. And the typical size was 10 feet. This was the largest size you could get, 12 feet. And these cost $1,000. Now these had been altered so as to allow you to steer them anywhere in the sky. And notice there are no gears. These are extremely inexpensive. $1,000, you had a fully steerable antenna, 12 feet in diameter. It worked up to frequencies of 15 gigahertz. And it was really, these are really marvelous things. And they cost $1,000. And a goal was established to create an antenna which was 1 hectare in collecting area, which is 10,000 square meters. And that would have taken about 1,000 of these. Now that's a big number, but not ridiculous. In fact, the manufacturers of these were quite prepared to build all 1,000 of them in a month, and we were able to fit them into 3 big semi-trailers. And we were almost ready to do that. But first, we did do this set to show that it can be done and that they can be connected together. Those 2 people standing there, one is Leo Blitz, who was the director of the Berkeley Radio Astronomy Laboratory at the time. This person, some of you may know something of that. It's Lynette Cook, famous space artist, who was doing the artwork for this thing. This is what it looked like. 7 dishes was the prototype array. This is what it looked like, and it worked just fine. And as a result of this, a proposal was made to Paul Allen, co-founder of Microsoft. There's a building named after him here. To fund the construction of the 10,000 square meter system. And he in fact produced the money to develop the whole design and technology, and promised $13 million to construct, because that was the estimate based on these as to what it would take. And so the Allen telescope array was, this is another picture of it. So the Allen telescope array was started back in around the year 2000. And it was to be a new generation of radio telescope, and in fact it is an extremely good way not only to get large collecting area, but the ability to make very sharp radio images of the sky. It can kill 2 birds with 1 stone. And this project in progress between the SETI Institute and UC Berkeley. It uses these somewhat odd telescopes for a reason, and that was, in his looking back from hindsight, this may not have been a smart thing. It was decided that we wanted to be able to observe any frequency in the microwave window at any time, because who knew where the SETI signals would be. And so we wanted a telescope that could do that. And to do that, you have to use a special kind of feed and collector antenna called a log periodic feed. How many of you have ever heard that? A log periodic feed. Ooh, I should have put in a slide which shows you one. They're very odd-looking things. They look like something very dangerous. But they can collect, are good antennas from all the way from less than 1 gigahertz up to 15 gigahertz. But they have a very long focal length, and as a result you have to use 2 reflectors to make it all work right. So this is why they look the way they do. And this shows you the ray paths. And I'll go back and do that again. The ray comes in, it's reflected off the main reflector, then to the secondary reflector, and finally focused on the log periodic feed. And this may look to you as though it's looking at the ground, but it's not. As you can see, this is when it's looking horizontally, because the incoming rays are horizontal. So it's looking at the horizon, but it looks as though it's looking at the ground. And this was adopted as the basic design for the Gallon telescope array. The reflectors are 6 meters in diameter, 20 feet in diameter. And they're made by taking big sheets of aluminum and pressing them against a mold with huge bladders full of water, just forcing them by the weight of the water to conform to the mold. And this way you make a very precise dish very easily. And there are actually 8 of them here, 8 of the dishes stacked and on a special carrier that was made to carry them from the manufacturer, which is in Idaho Falls, Idaho, to the site, which is at Hat Creek, which is 20 miles north of Mount Lassen in Northern California. And there they have been constructed, still being constructed, in a tent. And this shows one of the reflectors with the backup structure being attached. You can see on the left side a pedestal, which will hold up the whole thing when it's assembled. And here's one that's ready to be moved out and put on a pedestal. And there's a special machine that comes and picks it up, and takes it out of the tent. And here are 2 finished dishes with some very happy people, giving you a sense of the size of these things. The log periodic feed is not in place yet, so you don't see that here. And this is a more recent picture. Notice there are now shrouds, and this is to keep snow and water off from the focusing device and the electronics which are at the the feed system, the log periodic feed. And this is a current picture showing you that this is the total array as it exists. 42 antennas. That's as much as could be afforded, because what turned out here, and that's why I mentioned that going for all frequencies at all time may have been a mistake, is that these dishes are much more expensive than $1,000. And the result was that the amount of money provided by Paul Allen and some other gifts that have been received has only been sufficient to build 42 of them. And what's needed to make 10,000 square meters is 350. So 42 to go down and 308 to go. And right now, none are under construction because unfortunately, the recession has caused people to stop making gifts for things like this. And so we're stuck with 42. They are operating and they do just fine. They work very well, just as they are supposed to. Now, that's the present status of radio SETI, except for one thing I'll get back to in a minute. But along the way, a few years ago, it was recognized that maybe we should be looking for optical signals also. And what's the history there? The history is 50 years ago, 40 years ago, 30 years ago, the most powerful lasers we had on Earth were just things that made a few watts, couldn't possibly be focused into a bright beam that could be seen across many light years. And so it made no sense to search for optical SETI. And besides, the noise level, as I showed you, was larger at those wavelengths. But not for SETI. not for us folks, we folks, us folks. Yeah. There's some other technology under development, which is devices to create clean energy through nuclear fusion. And one of the prime approaches is being pursued at the Lawrence Livermore Laboratory, not far from here. And there they're trying to achieve nuclear fusion by heating a little capsule full of hydrogen to a temperature of about 10 million degrees, at which point it will fuse and you'll get out all the energy that you could get from a hydrogen bomb from that much stuff, and it's a lot. Now, this is, in principle, a very good system, but it's a challenge. You've got a little glass bead about the size of a BB. It's hollow. Inside of it, there's hydrogen gas. And you've got to heat that gas to 10 million degrees. As you do so, the pressure goes way up, and this thing's going to explode, obviously. So you've got to heat it up so fast that before the explosion can happen, it's already reached the temperature where it fuses. Well, how do you do that? You zap it with a laser beam, and it has to be really bright. And as it turns out, with even the best lasers they produce, it takes about 170 lasers all at once to zap the bead. Now, they've developed a laser called Helios, which creates a pulse of light whose power is an incredible amount. It's 10 to the 15th power watts, a petawatt. There's a new word for you today. A petawatt, 10 to the 15th watts, which is 1,000 times the total power production of all the electrical plants on Earth. So of course you can't do this very long. You have to turn off the Earth. And so the pulse lasts a billionth of a second, a nanosecond, but that's enough. In fact, you have to do it in a nanosecond, because after a nanosecond the whole thing's exploded and it's not going to work. And it takes 170 of these. And so at Lawrence Livermore there's a huge building the size of a football field with 170 of these lasers. And they're all carefully aligned, and they're going to zap this poor little bead any day now. They're ready to do it, and and hope to achieve ignition, as it's called. Well, that's all good, but to us what's interesting is this laser with its petawatt of power. And you say, well, wow, that's a lot. What happens if I take that petawatt of power and focus it into a narrow beam with a 10-meter reflector, as I have on Mauna Kea? Well, it turns out if you do the math, it's very simple. You create a flash of light which is brighter than a star for a billionth of a second. And not by a little bit, by about 1,000 times. Now, this is in the direction the beam goes. And so maybe the extraterrestrials are signaling us with these things, because it's so easy to detect. You don't need good signal-noise ratio. You don't even need big telescopes. And you can transmit signals hundreds, thousands of light years in pulses. Now, there are presently 3 projects going in the world. One of them is ours, another is at UC Berkeley, and the other is at Harvard. This is the start of our project. I just wanted to show you. You don't really need big modern things to do this. This is the first telescope at the Lick Observatory, not far from here, being constructed in the year 1888. This is the first building. Notice the lady here in her long dress. Here's another one with a parasol. That's what she's got. They've come to watch the goings-on at this operation. You notice the very proud guys standing bravely on top of the dome. And all of this is still there, by the way. If you visit Lick, you'll see exactly the same building, just the way you see it here. And when it was built, it had a 12-inch telescope in it. And it's still there. And this is the one we use for our optical SETI project. It now has in it, notice the dome is all wood, a 40-inch telescope, a 1-meter telescope, which you see here. And this was all built by Lick Observatory using cast-off scrap metal and things like that. In fact, a cast-off mirror, which was the center of the big mirror at Lick, where they had to cut a hole in the center so that the light could come out, and they cut out a circle 40 inches in diameter, and that's become the mirror in this telescope. And it is used in optical SETI. And optical SETI is very simple. A whole optical SETI detector can be built for about $2,000, because the stuff you need has been developed for nuclear physics experiments, and it's very cheap. The person you see here was an undergraduate student at UC Santa Cruz who built this as a senior project. She's now a PhD and a Hubble Fellow at UC Berkeley. And the way this works is you get photomultiplier tubes, which with 1 nanosecond time resolution and time response, and those are available. It's out of catalogs. And we don't use one, we use 3. We take the light and we divide it into 3 paths for a special reason, which was quickly learned to be necessary. The first one of these was built at UC Berkeley with 1 phototube, and it was a nightmare. And the nightmare comes about because you get false positives. What we're looking for is a burst of photons coming in. You'll be looking at a star, you'll be getting starlight, and then what we're looking for is a sudden added flash of light that lasts a nanosecond. And those happen due to cosmic rays hitting detectors, cosmic ray showers in the atmosphere, electrical discharges, corona discharge. And when the first, these were built both at Berkeley and Harvard, they had 1 detector, and they were getting positives every few minutes, and it would drive them crazy. They were detecting signals all over the place. So what you do here is divide the light into 3 beams and send it to 3 photomultiplier tubes. And in a case like that, you get a false positive in only 1 tube at a time. And so what is done is with the stream of pulses that come out of the photomultipliers are paired with each other in coincidence detectors, which are available very cheaply from nuclear physics. And these search for simultaneous arrival of photons at 2 different detectors, in this case 3. And in this way, false positives are eliminated because they don't arrive at all 3 detectors at once. But the thing we're looking for will arrive at all 3 detectors at once. And that's why the 3 detectors. And this works like a charm and is adopted at all the observatories doing this now. This has been used to search 6,000 stars for flashes of light, in each case only for 10 minutes each. Nothing's been seen yet. And it's slow going. And this one does have the downside that they have to be transmitting your direction or it isn't going to work. This shows our crew that works at the Lick Observatory. We're about to start a new project which will use 7 detectors for reasons that improve the statistics and so forth. And this is a team which involves the director of operations of the Lick Observatory, this fellow. This is Dan Wertheimer, genius at Berkeley, who designs all the detector stuff. This is the student Shelley Wright. This is me, if you didn't guess. And the biggest project of this kind right now is at Harvard. They have a 1.8 meter dish. It's a transit telescope. It has 64 detector modules, and it does not track. It just sits and the sky rotates through it. In this way, they search a huge swath of the sky for flashes every night. They're very proud of this 1.8 meter mirror because it's the largest telescope east of the Red River. Now, everything I've told you is optimistic. We're doing better and better. But we're learning that our paradigms change with time, and faster than you'd think. In one human lifetime, in 50 years, things have changed. We've all these years been looking for those narrowband signals, like the one I showed you in that waterfall plot. And now signals are changing so that they're not like that. And our detection algorithms in our computers are all looking for narrowband signals. And now we here on Earth are going away from narrowband signals. We send almost none now. And here's one that is an example. This is a picture I took a little over a year, it has to be over a year ago because I showed this last year. At Barrow, Alaska. This is United States Air Force Point Barrow long-range radar site. What this is a distant early warning radar, a BMEWS radar, which is used to guard against missiles coming from Asia towards the United States. And there's a super powerful radar in here, and this is one of a chain of these that exists. These are communication antennas which send whatever they see back to like Colorado Springs or something. And it's very interesting. was up there looking for a really quiet site to do SETI, and I found one. There's a place not far from here, not here, because this thing is not quiet. There's a place not far from here where there are no signals at all. It's like the far side of the moon. Perfect, beautiful place to build a radio telescope. We're talking about it. It's not it's not inhospitable as you might think. The whole temperature. This was in April. The temperature never got above 15 below zero, but you're dressed for it. It's not bad. You get used to it. This day I drove up to this thing. Right behind me was my car. In my car I had a big spectrum analyzer. I pulled this spectrum analyzer out of my car, and it's battery operated. I set it up and started measuring the spectrum of this radar, wondering when are the security people going to show up. They never showed up. There are no fences or guards or gates or anything. Where's the TSA when we really need them? It's so weird. I went there, I spent half an hour measuring the spectrum of this radar. And nobody came and said, "What are you doing there?" It's amazing. Whoops. This is the spectrum as observed there. This is from 800 megahertz, so 8/10 gigahertz up to 2 gigahertz. The hydrogen line is right in here. And this little bit you see here is in fact cell phones from Barrow, Alaska, which is right adjacent to this radar. This is the spectrum of that radar. Notice, not narrow band. And in fact, if you looked at it as time went on, you'd see the spectrum was jumping all over the place. It was narrow band at any given instant, but it was moving around over 100 megahertz. This is called spread spectrum. It's very common these days. It's used in almost everything. It's a way, in this case, it's used for military reasons. It's to prevent this radar from being jammed. But the same thing is used in cell phones, too, to allow people to share channels. Because when you're talking on a cell phone, there may be 100 other people all using the same frequency, but if you're using a different spread spectrum, the cell phone has the capability, which is very clever, of disentangling those signals and giving you only the one that's intended for you. So, spread spectrum. Our algorithms are not, our present algorithms in our search systems will not detect this. And that's a worry. We need to get our software people, and I know there are a lot of those around Stanford, to develop algorithms that are affordable and fast, which can detect things like this in the data. So that's one worry now. In 50 years, we've gone from one form of signal to almost entirely a form of signal we're not set up to detect. We've got to do something about that. Another thing which is happening, which is even more scary to SETI people, is that the Earth is slowly disappearing from the radio universe. This is the Empire State Building. It's got a big antenna on it that has about 20 TV antennas on it. An even bigger one is the Sutro Tower in San Francisco. If you've gone to San Francisco, you've seen this up on a hill. This thing is taller than the Washington Monument. You can see the scale of the houses here. It's about 100 feet taller than the Washington Monument. It's got more than 30 transmitters on it, and included in there is something like 15 television transmitters. And this shows you what's happened there. This is television stations, and just look at these UFH TV stations before we went to digital a few months ago. Notice some of them has had powers as much as 5,000 kilowatts, 5 megawatts of power. That's 5 times the power level of the Arecibo transmitter, except it's spread out, fanned out to the side. There's another 5 megawatt transmitter, 3 megawatts. This is what it took just to transmit television to rooftop antennas in the Bay Area, which is what this is for. Total power was 18 million watts being transmitted. This was the main sign of our existence to the universe. Now it says future digital stations because I made this slide before the transition happened. Now what we have is what you see here. You notice the power has gone down. The biggest power you see is a megawatt. We've gone from 18 megawatts to 5 megawatts.
Looks like KQED went up.
Oh.
Is this some comment about public radio?
Well, no, this was VHF, or were all lower power because they were easily, the antennas were more sensitive.
All right, so this is not political.
This is not a political thing. It's, I think you'll see the equivalent of all these. What's K-Pix here is 100 kilowatts. Over here it's, well, it's actually bigger. Well, all right. Forget it for a minute. Part of that's because they're changing their coverage area and stuff like that. But on average, the transmitter powers have gone down a lot. And what's worse is that none of this is narrowband. The old TV signals had a very powerful narrowband signal. Half the power was in the narrowband signal. This has a wide signal that looks like noise. And again, it's a signal that we would not be sensitive to with our search systems. And so our signals, which are being designed to not require so much power, but also to be in a form which is carries information more efficiently, are much more difficult to detect. Furthermore, we're being forced to share wavelength. There's only so much electromagnetic spectrum, so the spectrum has to be shared. And the prime example of that is the cell phone system, where hundreds and hundreds of people may be speaking on the same frequency at once. And to make that work, you have to have low power on the transmitters and many, many towers. Otherwise, that does overwhelm the system. Also, cell phones are, in many parts of the world, the only source of telephone systems now, because they're much easier to implement than something where you have to have wires or something all over the place. In many countries, third world countries particularly, the only telephone system is a cell phone system, and even the less wealthy people can afford them. And then, this is the worst news of all. This is the wave of the future here. This is the sort of satellite that sends television direct to homes on Earth, to 18-inch dishes on people's roofs. This is the Galaxy 1. It's a typical satellite that's used for that purpose. It's about 10 meters across, about 30 feet across. As you see, it has many little antennas to send television programs to different parts of the Earth. In fact, this one provides television to both North and South America. And it does it in an extremely clever way, and at very low power. Instead of 5 megawatts, typical power in one of these C-band and KU band are those are jargon for certain frequency bands, about 15 gigahertz. These are the bands that are used to send television to Earth. And look at the power, 20 watts, 75, 140. Not a million watts, 140. So down by 10,000 times fainter than what we had in the past. And all that power is being very cleverly on the Earth. This is the radiation pattern of Galaxy 11. This is the North American beam. Notice how it's tailored to feed Mexico, as it does. And Florida, it even has a little finger that points out to Puerto Rico. There's a finger for Hawaii. And so this is an extremely marvelous case of electrical engineering. There is a second beam which feeds South America too, which isn't shown here. This is the North American beam. So we're sending 20 watts straight onto the Earth, and almost all that's absorbed. The amount that goes back to space is maybe 1 or 2 watts. So instead of sending out millions of watts, we're now sending 1 or 2. And I suspect that within 100 years or so, this is the way all television will be delivered. It's just so efficient and so inexpensive. And we will turn off all those big towers with their megawatt transmitters, and the Earth will become very hard to find. And if that's the way of the world, or the way of worlds like ours, it means L. The L value may be only 100 years or so. And they'll still be there, just much harder to find. Now, what can we do about this? Can we make ourselves more sensitive? We can build bigger telescopes. This is one that's under construction, actually. It's being built by the Chinese. And it's to be 500 meters in diameter compared to Arecibo's 300. Same basic design. except that the entire surface is movable under computer control to make it into a parabolic shape instead of a spherical shape. And the energy collector is moved around by changing these cables. It's extremely challenging. I don't know if they can really do that. But it's under construction and supposedly will be finished in 2 years, which is really hard to believe. I asked the director, how are you going to do it in 2 years? He says, easy. Since we can mobilize 1 million men, give them all shovels and have them go do it. And they can. That's how the Three Gorges Dam was built, and they built that on schedule. So maybe we'll have this in operation in a few years. There's been efforts, suggestions that we should have a telescope on the far side of the moon. Good idea. It's the only place in the solar system that doesn't have the Earth in its sky at some time, and so is immune to radio interference from the Earth. We even picked out the crater on the far side that would work, right? And maybe in the future there will be something that creates a strong signal again to replace the ones that are quickly disappearing here. A prime example is solar power stations in space, which are now being seriously considered. One is actually under construction. And what one does is put solar panels, huge numbers of solar panels in space, and then use a big dish to transmit the collected energy to space as microwaves. And the proposed power levels are 1 billion watts, a gigawatt, which is typical of the ordinary coal-powered power stations on Earth. And all antennas are imperfect. They reflect a little, a few percent. So this thing may send 1 billion watts to Earth, but a few percent are reflected into space, and that's 10 million watts. So again, a strong signal. So maybe this is what will save us and allow us to detect civilizations. And lastly, I'm about at the end here. I'm just going to throw at you what I think is the ultimate technology that's going to change everything, which is the use of our sun as a lens. Now, how does that work? It works because gravity bends space. This is a result predicted by Einstein. It's a result of the theory of general relativity. The presence of a mass actually bends space. And that this actually happens was observed directly during a solar eclipse in 1915 and 1919, where the position of a star in the sky that was near the limb of the sun actually moved during the eclipse because the sun was bending space and deflecting the light rays. As you see here, the light rays that go close to the star are bent a lot. Well, it doesn't look like a lot, but it's a lot. Farther away, they're bent, but not as much. And the end result is the light rays are brought to a focus, and you create what is the most phenomenal telescope one can imagine. The sun acts just like a regular lens, except now your lens is over 1 million miles in diameter. It's got a big hole in the middle because the sun blots out a lot of the light. But still, if you work out the numbers, the total collecting area of one of these gravitational lenses is about equal to 30,000 Arecibo telescopes. That's at the radio wavelengths. It differs with wavelength. So 30,000 Arecibo telescopes. A resolution in the image is such that you can not only detect planets but photograph them in detail with these things. And you can detect the presence of cities' lights at night and all of that. So, why aren't we doing that? Well, a little problem. The focal point, big challenge, not a little problem, big challenge. The focal point, the closest focal point is 550 astronomical units from the sun, 14 times the distance to Pluto. And you can't really, these rays are interfered with by the atmosphere of the sun. You really have to go out probably to 700 AU before you get sharp images. Now, that means you have to put a spacecraft out there, and we don't have the capability of doing that. We need nuclear-powered spacecraft to do this. But you can predict that 100 years from now we will do this. And I would predict that every civilization does this because it is such a powerful instrument for studying the universe, better than any optical or radio telescope you can imagine by a huge margin. You got a lens a million miles in diameter, and you can use it to capture radiation from distant objects. Here's the source. This is a sketch, of course. Here's the lens. It's a thick ring focusing all the radiation to your spacecraft, which is 700 AUs from your star. This would allow you to study the universe in incredible detail on any wavelength that you instrument this spacecraft for. This, by the way, is called the Einstein ring. You may see that if you read the literature. And it could be used as a communication link. Spacecraft at each end. This one shows us using one star as a lens, but you could use one at the star at each end. And if you work out the math for that, it's just incredible. You can almost hear a cell phone between two stars with two such lenses, each amplifying the signal by tens of thousands of times. A few watts is all it takes to make a detectable signal between two stars. And if this is what civilizations do, and once you realize this is possible, as soon as we can get spacecraft out to this great distance and maneuver them around, it's what every civilization will do. And in the end, it means there's probably a galactic internet made by interconnections between gravitational lenses. All civilizations can learn about each other in this way. And to me, this is the answer to the Fermi paradox. You can learn everything you want to about a civilization because you have such good communication, such good capability to capture data. You don't need to send spacecraft at all. You all do it this way.
The problem is we're just not on the grid yet.
We're not on the grid, but we're 100 years from now. A blip in cosmic time will be on the grid. And there's probably tens of thousands that are on the grid right now, waiting for us. And they're not all that anxious. They got plenty of sources of information, as it is. And
that was amazing. Would you consider taking a few other questions? I'm sure there are people who want to ask questions about your conception of what an alien would look like. And when are we going to find one? Should we see Contact? Should everyone run out and get it on Netflix this week? Anyone want to start? I'm sure there are lots. Go ahead.
So at the very beginning, you mentioned the whispers that came through the radio signals from Earth sources. I was wondering if there's any analogs that do that on an auditory level from just phenomena in space that you've identified as not extraterrestrial, but also not as an Earth source.
I don't think there's any auditory sound sources like that. The whispers are all caused by lightning. Lightning makes radio waves at all wavelengths, and the lowest frequencies, these get trapped in the magnetic field and travel back and forth from one side of the other. And the different frequencies travel at different speeds, which is why you get a whistle. The lowest frequencies come last. Highest frequencies first. Goes out of frequency. But I don't think there's any equivalent in the audio spectrum.
Would it be possible to use the gravitational lens concept with a smaller body, say like Jupiter, where we wouldn't have to be 250 AUs out?
There's a simple formula which I carry in my head, but it's simple, which tells you what that minimum focal distance is. And it depends greatly on the mass. The mass of Jupiter is 300 Earths. It's less than 1,000th that of the Sun. So the distance of the focal point is in fact very far. And the size of the Einstein ring is much smaller, so that's not good. However, where that the comment really applies is to white dwarf stars and neutron stars. Neutron stars have their first focal point about, as I recall, an AU from the star. They are imaging their whole planetary system. And I've always thought the pulsar observer should be looking for this. Because as the planets go around the neutron star, at some point, the neutron star will be actually imaging them in our direction. We should see the presence of the planet. And nobody's ever looked for that. It's probably in the data that people have discarded as trash. And the same deal with white dwarfs. The nearest focal distance is so close that they can image their own planets. Neutron stars are stars that are 10 kilometers in diameter, so they're close, and they have the mass of the sun, so the bending is really great for the rays that pass close to them.
Could you use a black hole for that?
That's great too. Black holes do fine.
My quick question, you talked about how the Earth's presence may be sort of disappearing because we're changing our technology and all that. So maybe, as far as SETI is concerned, or maybe NASA, is there any sort of priority as far as kind of going to try to detect extraterrestrial signals versus trying to maybe intentionally put them out for detection? But
that's a big subject right now. I send a signal, but I don't believe we should send signals because it's better to use our resources to listen. I'll tell you why in a minute. But there is a lot of people now proposing that we should sort of have a moral obligation to send signals. If we're going to listen, we should be compensating or rewarding people sending us by sending them something. And so there are a lot of proposals to do what's called active SETI, which is that we transmit. And we do more of things like the AAC message. The reason I don't think this is a good idea is, first, we're doing that, at least for a while, through our television broadcasts, tremendously copious. There's a cacophony of signals leaving the Earth that somebody with a gravitational lens can easily pick up. The second reason is that sending is expensive, and I think it's better to put the resources, financial and otherwise, into the searching. There's a third reason given by people which I don't buy into because maybe it's because I'm an optimist, and that is that maybe it's dangerous. The analog they put is that if you're in a jungle at night and you know there are dangerous creatures out there, it's best to be quiet, very quiet. You don't shout in the jungle at night. And there's this idea that perhaps if they know of our existence, they will come and attack us for fear that we will do it to them. There's a good, strong argument why nobody's ever going to attack anybody else, which is that energy argument that I gave you with the interstellar rockets and such. There's no way another civilization can attack another without using resources far beyond any that would be acquired or preserved by making this attack. So I think space, in a way, quarantines us from one another so we can't attack. So even if they are aggressive, they're not going to attack, even though we're shouting in the forest at night. Particularly since our shouts probably should be seen as friendly. So these are the reasons why I don't think sending messages is a good idea, particularly as long as we are sending signals ourselves, as we are. We're already doing it free of charge.
How long would it take to move a like communication spaceship out to 700 AU?
Well, with our present spacecraft, chemical rockets, our most distant spacecraft is 120 AUs out, so a fifth of the way, and it has been traveling 30 years. So it's going to take another 150 years, 120 to 150 years to get to that distance, which it will. So that's not very appealing to people with 60 or 80-year lifetimes. So what I think to make this appealing to those who would fund such a project, you've got to figure out the propulsion system that can get you faster. Those have been on the drawing board for years. They've been nuclear rocket engines that have been designed, ready to put together and test.
For more, please visit us at stanford.edu.